Good morning again, everyone. It's nice to see you all. My name is Zhi. I'm a final year PhD student in Matteo's group from Utrecht University. In my PhD, I mostly work on improving the computational efficiency of energy system optimization models. Well, computational efficiency has become, nowadays, as the systems becomes more and more complex, the bottleneck to have solutions for the energy system optimization. For operational problems, for example, we have the electricity system. It requires fast responsive decisions. It requires a power balance within seconds, not even milliseconds. For investment problems, those decision makers, they're often interested in having uncertainty facing the uncertain future. There, they make investment planning for dozens, tens, if not hundreds of scenarios. And in each scenario, they want to see multiple years how the system evolve through the years and when is the right time to make system change. All of these make it a higher and higher demand for fast, reliable, and hopefully optimal solutions, and that requires higher and higher computational efficiency. Today, I'm here to share with you our latest work. It's called Error-Free Model Reduction with Low-Resolution Precursor Surrogates. It's very has a lot of huge gain in computational efficiency. It doubles the speed. At the same time, producing the full resolution, zero error solution. So I'm very excited to share with you. I know it's a bit counterintuitive. In the literature of computation, we have this, there is no free lunch theorem. If we want to improve the accuracy of something, we need to either sacrifice by having more complexity or sacrificing the accuracy elsewhere. That's how I generalize it. However, in this work, we show that there are free lunches, and not only free, big lunches. And we discuss briefly why this is groundbreaking, and I will also introduce how we achieve this. And in the end, we look forward to the future study directions. So this is one of the results we get. All of the colored bars, including the grayer ones, you see are the computing time. And you can see that, so on the x-axis is the temporal resolution for the surrogate. And by using different surrogate resolution, we reduce the full model into reduced model. And then the reduced model takes much less time to solve. And even if we include the time used to solve the surrogate, it's still more than double the speed in the solution, in solving the optimization problem. And all of the instances here, using our error-free reduction, comes at no modeling error, no reduction error. Why this is groundbreaking? This is from our previous work. Now it's published. You can access. What we often see is that we build optimization models for the energy system, and the solution qualities are bounded by the temporal, the details, the levels of details, including temporal discretization, spatial discretization. And in this work, we make the temporal resolutions fully flexible. Traditionally, we have part of the system, or the whole system in a uniform, fixed temporal resolution that can be redundant for several parts. Then we come up with this flexible resolution. I gave an example. Say we want to make decisions for the energy system in Austria. We have high resolution. We want to have a very exact solution, high quality solution. But we don't want that amount of high resolution, for example, in Spain, in farther countries. However, this is a connected grid. We still need to have them. Then in this work, we show that by having this geographically decreasing resolution, higher resolution in the target country, Austria, for example, and lower resolution in the neighboring countries, we are able to break this Pareto front. What is this Pareto front? When we have high resolution, normally speaking, in uniform resolution, we pay more for higher accuracy. And we have a rougher model, then it's cheap, but it comes at huge error. And there, with this flexible resolution, we can we break further into by having at the same time faster to solve and more accurate solution. But this is again follows there is no free lunch theorem. You can see that it's very good on the target country. The orange one is the target country, has very small error, but then it comes at a cost of the whole system because there we have lower resolution to reduce the computational time. From there, we have this question. Yes, it's good. We push the Pareto front. But how is it possible to do it for good? To have error-free reduction? And recently we find that, yes, if we just reduce the redundant variables. By redundant, I mean those values of the decision variables in the optimal solutions are easily known or detectable. So let me just give it a very simple example. I don't give any equations for now. Just save our eyes for the moment. We have 5 generation units producing to meet a demand. And we sort them by cost, from below to high. If we minimize the total production cost, then for sure, the cheapest or cheaper units are first being dispatched. They produce until the final unit that meets the demand. And we know for sure that those units producing at full capacity, there are units producing at full capacity, there are units producing at zero, they're idle, and there are units producing at the partial capacity, which is the blocks overlapping with the dispatch solution or the demand. And in the earlier study, we used low resolution to aggregate the times. Now, we thought of this idea. How about we use the low resolution models as a surrogate? And they are just there to remove the variables. They don't solve it yet. They tell us which are the variables that are for sure producing at full capacity. For example, if we look at a time window of 4 hours, and we examine the best scenario, the lowest demand hour, if in that hour there are units producing at full capacity, we know for sure other higher demand hours, those are producing at full capacity. And vice versa. In the highest demand hour, we don't need those units. Those units are not needed for the full window. And similar logic when we have variable renewable energies, then that the best scenario becomes lowest demand, highest renewable availability, most wind, most solar, sunlight, and vice versa. And here we have this mathematical formulation. In this work, we want to have aligned the case study together with the mathematical formulation as well as the mathematical proof. Yes, we have a mathematical proof. And this is an economic dispatch of national energy systems, for each country, for each time step, for each technology. And the surrogates are in the same formulation, just that they are in low resolution. And instead of the capacity values, instead of original capacity and the demand values, we use the min max values for each time window, as I discussed earlier. And we also, in this work, we also provide mathematical proof that we do have this preservation of accuracy. On the left, these are led by Michael Risma, who is also present today. She wrote one theorem, one corollary. This theorem basically says there must be optimal solutions within the surrogate bound, given that we found the surrogate bound. And the second, the corollary says we can use low resolution surrogates for this purpose. This is implementation. It's very small in font size. And we start with the full model. And then for the full model, we pick a low resolution to construct a surrogate, and then we solve the surrogate. Now with the solution of a surrogate, we loop over the time steps, and for each time step, we look at each country, and each country look at each generator, whether they are in the two states. They're idle, or they are producing at full capacity. If so, they are redundant, and then we remove it from the full model. At the same time, we also consider that if later on you'll see, if we have a complex enough surrogate itself can be hard to solve. Then how about if we start from simple and adding the complexity of the surrogates, we solve the surrogates in serial way instead of individually. Then we also loop over a list of surrogate resolutions. To showcase the effectiveness of our method, we built this case study based on TYNDP 24 publication. It's the economic dispatch of 35 European energy systems. And we picked 2 years to show one is most stable and one is most fluctuating. To be clear, there's no energy storage, there's no transmission lines between the countries, but we have strong belief that these will be applicable to those features as well. And again, for both years, there are significant gains in computational efficiency, and as well the memory usage. You'll see later on how much the decision variables are reduced. And we can make some observations here. One is that if we reduce on the upper, for low resolution, if we reduce on the upper side, it's more effective than reducing on the lower side. What does it mean? It means for some seasons, for some months, some expensive units are not being used at all. Then it's very effective by just removing them out of the problem. However, when we go to higher resolution, then the effectiveness of removing upper side, lower side becomes similar. Yet there's still a combinatorial effect. Removing them at the same time give us even more efficient solution. Again, all of the instances are error-free. Like I said, there are no energy storage, no transmission. This gives us actually a very, very nice test field to see how our method is effective for different kinds of energy systems. You can see these are all European countries, and in the scenarios they are decarbonized in different extent. And we see that in general, for all of the systems, as you can see, we have huge reductions, significant reductions from 1% the full model, all of the variables, to more than half of the decision variables. And by looking at specific examples, Estonia and Czech on top, Estonia and there has more varying renewables, then it's relatively speaking harder to reduce than the Czech, which is more stable, mostly dominated still by fossil fuel. Similar can be found for Spain and Malta. There in Malta, as we go further on higher resolution, it directly reduces to some level and then stays there. And between the climate years, again, when we have more varying climate year, it's relatively speaking a little bit harder to remove. For example, this one, Bosnia, and here, when we have more stable year, oops, it reduces more. Okay, this bring me to the conclusion. To overcome the efficiency accuracy trade-off, there are big free lunches, and we explained why this is groundbreaking, and hopefully I showed clearly enough to you how we achieve this. And more on the way, we aim to extend to include more system features, like I said, energy storage, network transmission, and this is also a good chance that we rethink how we use the computing power. If we just solve the problems in brute force, that's what we get. However, if we use it more intelligently, like to reformulating the problem, like this one, we could achieve double the speed with the same amount of computing power. Okay, so this is work we have already submitted. Let's keep in touch, in case I will also be open for future opportunities. Thank you.